The boundary element method, which is also known as the boundary integral method, is a well-established numerical technique for solving boundary value problems in science and engineering. It is based on approximating boundary integral solutions of partial differential equations. In the boundary element method, only the boundary of the solution domain is discretized into elements. For a two-dimensional problem, the boundary is a line which can be easily discretized into elements. To discretize it, put closely packed points on the line, and join two consecutive points to form straight-line elements. For a three-dimensional problem, the boundary is a surface, which may be discretized into plane elements. Unknown functions on the boundary are approximated using simple functions, such as constant or linear functions, over each of the elements. The smaller an element is, the better the approximation is. This video lesson introduces the boundary element method through solving a boundary value problem governed by the two-dimensional Laplace's equation. It comprises two parts. The first part shows how a boundary integral solution can be derived for the two-dimensional Laplace's equation. The second part shows how the boundary integral solution can be used to derive a simple boundary element procedure for solving the boundary value problem approximately. We will introduce the boundary element method through the boundary value problem here. Solve the Laplace's equation, del 2 phi over del x square, plus del 2 phi over del y square, equals 0, in R. Phi is a function of the Cartesian coordinates x and y. Here is a sketch of the solution domain, R, on the OXY plane. R is bounded by a simple closed curve C. For specifying the boundary conditions, the curve C comprises two non-intersecting parts denoted by C1 and C2. Here are the boundary conditions on C. Phi equals f1xy, on C1, where f1 is a given function of x and y, del phi, over, del n equals f2xy, on C2, where f2 is a given function of x and y. The normal derivative, del phi over del n on C, is defined by del phi over del n equals nx times del phi over del x, plus ny times del phi over del y, where nx and ny are, respectively, the x and y components of the unit vector that is normal to C, and points out of R. Note that nx and ny may vary from point to point on C. Either phi or del phi over del n, not both, is specified at each and every point on C. At a given point on C, if phi is known, then del phi over del n is unknown, or vice versa. We will show how a boundary integral solution can be derived for the two-dimensional Laplace's equation. We start by looking at the fundamental solution of the two-dimensional Laplace's equation. In Cartesian coordinates, the two-dimensional Laplace's equation is given by del 2 phi over del x square, plus del 2 phi over del y square, equals 0. Phi is a function of x and y. The polar coordinates r, and theta, centered about the point 0, 0, are related to the Cartesian coordinates x and y, by x, equals r, cos theta, and y, equals r, sine theta. We introduce the function psi r, theta, equals, phi, r, cos theta, r, sine theta. In the polar coordinates, the two-dimensional Laplace's equation can be written as 1 over r, times del over del r times del psi over del r, plus 1 over r square, times del 2 psi over del theta square equals 0. If psi is independent of theta, that is, if psi is a function of r alone, we can write d over dr, r times d psi over dr, equals 0. We can integrate this ordinary differential equation twice to obtain psi r equals a times natural log r plus b, where a and b are arbitrary constants from the integration. Hence, phi xy equals a times natural log x square plus y square to the power half plus b is a solution of the two-dimensional Laplace's equation everywhere, except the point 0, 0. If we shift the center of the polar coordinates from the point 0, 0 to the point psi eta, we can write phi xy equals a times natural log x minus psi square plus y minus eta square to the power half plus b. This function is a solution of the two-dimensional Laplace's equation everywhere, except the point psi eta. Let the constant a be given by 1 over 2 pi, and b by 0. This gives us the particular solution, phi xy equals 1 over 4 pi times natural log x minus psi square plus y minus eta square. This particular solution plays an important role in the boundary element method. We denote it specially by capital Phi. We write capital Phi xy xi eta equals 1 over 4 pi times natural log x minus psi square plus y minus eta square. We refer to the function capital Phi as the fundamental solution of the two-dimensional Laplace's equation. We will show how it can be used, together with a reciprocal relation for solutions of Laplace's equation, to derive a boundary integral solution. We derive here the reciprocal relation that can be used together with the fundamental solution to obtain a boundary integral solution for the two-dimensional Laplace's equation. Let phi 1 and phi 2 be any two solutions of the two-dimensional Laplace's equation in the region R, bounded by the simple closed curve C. Since phi 1 and phi 2 are solutions of the two-dimensional Laplace's equation, we can write del 2 phi 1 over del x square plus del 2 phi 1 over del y square equals 0. Del 2 phi 2 over del x square plus del 2 phi 2 over del y square equals 0. These equations are valid at points in the region R and on the curve C. Multiply the first equation by phi 2, and the second equation by phi 1, and subtract one of the resulting equations from the other to obtain del over del x, phi 2 times del phi 1 over del x, minus phi 1 times del phi 2 over del x, plus del over del y, phi 2 times del phi 1 over del y, minus phi 1 times del phi 2 over del y, equals 0. We integrate the equation which we have just obtained over the entire region R. We apply the two-dimensional version of the divergence theorem to transform the double integral over R to a line integral over C. We obtain integral over the curve C, phi 2, times del phi 1 over del n, minus phi 1, times del phi 2 over del n ds equals 0. This integral equation here gives us a reciprocal relation between any two solutions of the two-dimensional Laplace's equation in R. We will now use the fundamental solution and the reciprocal relation for the two-dimensional Laplace's equation to derive a boundary integral solution for the boundary value problem under consideration. Let phi 1 equals capital Phi xy xi eta, the fundamental solution, and phi 2 equals phi xy, the desired solution of the boundary value problem. Since capital Phi xy, xi eta is not well defined at the point xy equals xi eta, we can apply the reciprocal relation for solutions in the domain R, and the boundary C, only for points xi eta that lie outside R and C. Hence, we obtain the boundary integral equation, integral over C, phi times del capital Phi over del n, minus capital Phi times del phi over del n, ds, equals 0, 4, xi eta not in R union C. Boundary integral equations, which are more interesting and useful than this one here, can be derived for xi eta in the interior of R, or on the boundary C, by modifying appropriately the domain for the solutions in the reciprocal relation. Consider the case where the point xi eta lies in the interior of the region R. We cannot apply the reciprocal relation on the desired solution phi, and the fundamental solution capital Phi, in the region R. This is because capital Phi is not well defined at the point xi eta, which lies in R. To apply the reciprocal relation, we modify the region R, to one that does not contain the point xi eta. Let C epsilon be the circle centered at the point xi eta, and having radius epsilon. The radius epsilon is sufficiently small, so that the circle lies entirely inside the region R. Let R' be the region between the circle C epsilon and the curve C. Since the desired solution phi and the fundamental solution capital Phi are solutions of the Laplace's equation in R', we can apply the reciprocal relation on them in R'. The boundary of R' comprises the circle C epsilon and the curve C, hence, the boundary integral equation in the reciprocal relation contains an integral over the circle C epsilon, in addition to the integral over the curve C. We can recover the original solution domain R, in a limiting manner by letting the radius epsilon approach 0 plus. As epsilon approaches 0 plus, the region R' tends to the solution domain R. Hence, we evaluate the limit of the integral over C epsilon as epsilon tends to 0 plus. We will now evaluate the limits of these integrals over the circle C epsilon as epsilon tends to 0 plus. Let us define the polar coordinates r and theta, centered about the point xi eta, which is the center of the circle C epsilon. R and theta are related to the Cartesian coordinates x and y by x minus psi equals r cos theta, and y minus eta equals r sine theta. In the polar coordinates r and theta, the circle C epsilon is defined by r equals epsilon, for theta between 0 and 2 pi. The length of an infinitesimal portion of the circle C epsilon is given by ds equals epsilon d theta. On the circle C epsilon, the fundamental solution capital Phi is given by capital Phi equals 1 over 2 pi, times, natural log epsilon, and the normal derivative of capital Phi by, del capital Phi over del n, equals minus 1 over 2 pi epsilon. From the Taylor series of the function phi xy about the point xi eta, we find that phi xy equals phi xi eta plus O epsilon terms at point xy on the circle C epsilon. From the information that we gather on the circle C epsilon, we find that, integral over C epsilon, phi, del capital Phi over del n, ds, equals minus 1 over 2 pi times, phi xi eta, times, integral from 0 to 2 pi, d theta, plus, O epsilon terms. Which reduces to, minus, phi xi eta, plus, O epsilon terms. Similarly, we find that, integral over C epsilon, capital Phi, del Phi over del n, ds, equals, O epsilon, natural log epsilon terms. Hence, the first integral tends to, minus, phi xi eta, and the second integral tends to 0, as epsilon tends to 0 plus. Recall this equation obtained from the reciprocal relation for the point, xi eta, in the interior of the region R. We have just evaluated the limit of the integral over the circle C epsilon. The value of the limit is, minus phi, xi eta. Hence, we obtain, phi, xi eta, equals, integral over C, phi, del capital Phi over del n, minus, capital Phi, del Phi over del n, ds, for point xi eta, in the interior of the region R. This gives us, a boundary integral formula for computing phi at any point xi eta, in the interior of the region R, if phi and del Phi over del n, are both known at all points on the boundary C. Lastly, we derive the boundary integral solution for the case where the point xi eta lies on the curve C. The fundamental solution capital Phi is not well defined at the point xi eta. To apply the reciprocal relation, we modify the boundary C and the domain R to exclude the point xi eta on the boundary. As before, let C epsilon be the circle centered at the point xi eta and having radius epsilon. Let D be the part of the curve C outside the circle C epsilon, and d epsilon be the part of the circle C epsilon inside the region R, union, C. R, prime, is the region bounded by the simple closed curve D, union, d epsilon. Since the point xi eta lies outside the region R prime, we can apply the reciprocal relation on phi and capital Phi, in R prime. The reciprocal relation gives us this integral equation, which involves integration over the curves, d, and d epsilon. Note that the curve d approaches the curve C, as epsilon tends to 0 plus. If the point xi eta lies on a smooth part of the curve C, then the curve d epsilon approaches a half circle, as epsilon tends to 0 plus. Assume that the point xi eta lies on a smooth part of C. In working out the integral over the curve d epsilon, we are integrating over a half circle, if we let epsilon tend to 0 plus. Hence, the integral over d epsilon tends to minus half phi xi eta, as epsilon tends to 0 plus. We obtain the boundary integral solution, half phi xi eta equals integral over C phi del capital Phi over del n minus capital Phi del Phi over del n ds for the point xi eta on a smooth part of C. Here is a summary of the boundary integral solution, or boundary integral equation, for the boundary value problem governed by the two-dimensional Laplace's equation. We will derive a boundary element method, based on this boundary integral equation, to solve the boundary value problem approximately. Recall the boundary value problem of interest in this video lesson. We will now show how the boundary integral solution or equation can be used to derive a boundary element method for solving this boundary value problem approximately. Let us look at the boundary integral equation for the point xi eta in the interior of the solution domain R. The fundamental solution capital Phi, and its normal derivative del capital Phi over del n, are known functions. If the desired solution Phi, and its normal derivative del Phi over del n, are known on the boundary C, we can compute Phi at any interior point xi eta, in the solution domain R, by evaluating the line integral over C. However, the boundary conditions of the boundary value problem give us only either Phi, or del Phi over del n, not both, at each and every point on C. At a given point on C, if Phi is known, then del Phi over del n is unknown, or vice versa. Hence, we have to find Phi, or del Phi over del n, whichever is not given by the boundary conditions, on C first, before we can use the boundary integral equation here to compute Phi, at any interior point xi eta, in R. We will now show how the boundary integral equation for the point xi eta, on a smooth part of the boundary C, can be used to determine approximately unknown Phi, or del Phi over del n, on C, whichever is not given by the boundary conditions. Here is the boundary integral equation for point xi eta, on a smooth part of C. We start approximating by discretizing the boundary, C, into straight line elements. We put n well-spaced out points on C, and join two consecutive points to form n straight line elements. We denote the straight line elements by C1, C2, and so on, until Cn-1 and Cn. The boundary, C, is approximated as being made up of the n straight line elements. We show here how C is discretized into 6 elements. To devise a simple boundary element method for solving the boundary value problem approximately, we approximate Phi, and its normal derivative del phi over del n, over each of the straight line elements, by using constant functions. More specifically, we make the approximations phi equals approximately phi k, and del phi over del n equals approximately pk, for point xy, on the straight line element ck. Phi k and pk are, respectively, the values of phi and del phi over del n at the midpoint of the element ck. For a given k, we know the value of either phi k or pk, not both, from the boundary conditions of the boundary value problem. Let us now approximate the integral over C in the boundary integral equation for the two-dimensional Laplace's equation. The integral over C is approximated as the sum of integrals over all the straight line elements. The functions phi and del phi over del n are approximated as constants over each of the elements. Hence, the integral over C is approximately given by sum over k from 1 to n phi k times integral over ck del capital phi over del n ds plus sum over k from 1 to n pk times integral over ck capital phi ds. Since capital phi and del capital phi over del n are given functions, the integrals over ck are known. Analytical formulas for evaluating the integrals are given in the book, A Beginner's Course in Boundary Element Methods. This is the constant element approximation that we have just obtained for the boundary integral equation. Either phi k, or pk, not both, is known for a given k. If phi k is known, then pk is unknown, or vice versa. Hence, the right side of the discretized boundary integral equation contains n unknown constants. Let us now collocate the discretized boundary integral equation by taking the point xi eta to be the midpoint xi m, eta m of the element Cm. Note that the midpoint xi m, eta m lies on a smooth part of the element Cm, not at what may be possibly a corner between two neighboring elements. Hence, lambda equals half at the midpoint xi m, eta m. We obtain a system of n linear algebraic equations in n unknowns. We may bring all terms containing the unknowns to the left side, and all other terms to the right side, in order to write the equations in matrix form, A, x equals b, where A is a known n by n matrix, x is an n by 1 matrix containing the unknowns, and b is a known n by 1 matrix. The system can be solved for either phi k or pk, whichever is not given by the boundary conditions, for k equals 1, 2, and so on until n. For details on programming the linear algebraic equations, one may refer to the book, A Beginner's Course in Boundary Element Methods. Once phi k and pk are completely known for k equals 1, 2, and so on until n, we have solved the boundary value problem under consideration. We can now compute the desired solution phi at any point in the interior of the solution domain R by using the approximate formula here.